So there you go, that really sets the tone there. It's lovely to see Nathan and Gordon Bell, who I interviewed a couple of years ago in San Francisco, amazing guy. So let's get our first speaker up onto the stage. It's a real pleasure to introduce Andrew Blake, who's the Managing Director of the lab here. Many of you will know him. He's for many years been a computer vision expert, and his technology was there lurking, waiting until a certain project, Natal, began to be spoken about. Then there was a synergy, amazing thing happens, and well, the rest was kind of history, but also the future as well, as we'll be hearing as well. So it's a real pleasure to introduce Andrew to the stage. Let's give him a warm welcome. Andrew Blake.
Well, it's great to see you all here. Thank you for coming to help us celebrate our 20th anniversary. Of course, it's not the 20th anniversary of Microsoft Research Cambridge. This is the 20th anniversary of Microsoft internationally. And as my colleague Peter Lee, who's the director of the lab in Redmond, just said, it is indeed the case that the sun never sets on Microsoft Research. And here you see all of our labs across the world. We're the principal European lab here in Cambridge. We have innovation centres in Germany, in Egypt, and now in Israel, and also joint labs in France, Italy, and Spain. The events of the day began rather early at a shocking 2 a.m. with Chief Research and Strategy Officer Craig Mundy speaking here in Beijing, and the celebrations then moved on to our lab in Bangalore. Now we've got to Cambridge. After us, there'll be the New England lab in Cambridge, Massachusetts, Silicon Valley, and finally the mothership here back in Redmond. So 20 years, we were founded in 1991. The company only had a few thousand employees at the time, and Bill Gates and Nathan Myhrvold, who you just saw on the movie there, took a proposal to Microsoft's board of directors that to take Microsoft into the future, we were going to need basic research in computer science. And it took only a short while to accept this proposition, and Nathan Myhrvold then hired Rick Rashid, who's our chief research officer, and they got started. They wrote the mission statement for Microsoft Research, which I think we can take some pride in saying has not changed from then until now. And I think the remarkable thing about it is that many industrial research labs begin with the proposition that you need research to feed technology into products. And Microsoft Research doesn't begin with that proposition. We begin rather with the idea that you need a powerhouse of expertise in basic research. And so first and foremost, the Microsoft Research Labs are about being experts and at the forefront in the areas that we cover. And from that emanates, I have to say largely by serendipity, transfers of ideas into products. And you never know which of the things that you work on are going to turn out to be influential on the company landscape. And this is why I think it is so important that the research lab is based on a foundation of fundamental research with the technology transfer following on. And the third tenet is that with a company like Microsoft, you don't know what you're going to be doing in 20 or 30 years' time. What company can know that? And so you need a body of people who are going to be well placed to try to work out what the future, in this case of computing, will hold. The lab in Redmond had been running for about 5 years when Nathan Myhrvold, Rick Rashid, Chuck Thacker met Roger Needham in San Francisco. Roger, of course, was the head of the computing lab here in Cambridge at the time, in the university, and they met to discuss the idea of setting up a lab here in Cambridge. And the idea was that, by that time, Microsoft Research was already gaining a lot of recognition, particularly in computer graphics, programming languages, becoming established as a major force in computer science. But of course, not everybody who wanted to work with Microsoft Research wanted to move to the west coast of the US. And so it seemed to make sense that in order to tap the talent and its geographical predilections, that something should be set up in Cambridge. And Nathan instructed Roger Needham that if every project you start succeeds, then you'll have failed. And with that dictum behind him, he started the lab up in 1997 and was head of the lab from then. My colleague Andrew Herbert took over in 2003 and just recently retired, and I'm his successor. So when you're starting up a lab, who do you hire? Well, Roger started hiring at what you might think of as the core of the discipline of computer science. And his first hire was Luca Cardelli, who was a scientist in the DEC lab in Palo Alto, who came to set up the Programming Principles and Tools, PPT group, here. And very shortly afterwards, we hired Andy Gordon, who was a Royal Society Research Fellow here at the university. And one of the first things that they did, an early contribution, was their 2000 paper at the Popple Conference on Mobile Ambience, which is all about establishing the semantics of computing which has a locality associated with it. So this was, in a way, a natural idea to bring formal methods to the problem of computing in different locations, just as mobile computing was becoming influential. And I'm very happy to say that just last year their paper was voted as the most influential paper from 10 years back at the Popple Conference. And the citation said that it led to applications of concurrency theory in fields as diverse as security, safety-critical applications, query languages for semi-structured data, and systems biology. And that last one, systems biology, is really a bit surprising, and this is something that I'm going to come back to, which is that the formal methods, the canon of formal methods and its arsenal, if you like, has had a very surprising influence, not just here, of course, but this is something that's happening around the world on understanding biological systems. For example, we have Byron Cook and Jasmine Fisher working here together, also Alex Taylor, on modeling systems of cells in skin. And it turns out that formal methods actually look set to illuminate how such systems actually work, and you'll hear about that in the panel that follows on from my talk. What else have we got in Programming Principles and Tools? Well, there's a kind of spectrum of people, and I think there's a principle behind this as well, which is that we maintain an ecosystem, if you like, of research styles where some people are working in a rather theoretical way and others are very applied. And so let me illustrate that spectrum in the programming group. We have Georges Gontier here, who, by the way, has just won the rather prestigious EADS Foundation Grand Prize in Computer Science. One of the things he's particularly well known for is his proof of the four-color theorem, which dates back a few years now. And you may wonder why anyone would be needing just a few years ago to prove the four-color theorem. Wasn't it already done back in the 70s? And that is indeed the case. It was, and indeed with the use of computers, because it was something that you simply couldn't prove entirely by hand. But that proof from the 70s is something which is extremely difficult to check, because it's an unholy mixture of pieces of mathematical reasoning combined with combinatorial checks run by the computer, and for a mathematician to sit down and verify all of that to their satisfaction is very difficult. Whereas the new style of proving mathematical results that Georges is pioneering is based very much on automated theorem proving. Here you have a statement of at a high level, if you like, of the four-color theorem. There's the theorem itself at the bottom right, and then some of the definitions that you need to contribute to the theorem, and so on. And in some sense, an expert can look at this statement of the four-color theorem and check that all looks well simply by looking at that panel. So that is a very different beast than the original proof of the four-color theorem. And of course, also in doing that, our capability in automated theorem proving is being stressed and stretched and developed. At the other end of this spectrum that we have in the Programming Principles and Tools group, there's work on functional programming. Recently, Simon Peyton-Jones and Simon Marlowe got the 2011 ACM SIGPlan Award for their work over a number of years on Haskell, which is a functional programming language which is used not so much for implementing systems, but for understanding and pushing forward, or is it backwards, the nature of functional programming and for advancing basic understanding and developing ideas. Don Syme, who's pictured here, has done something very influential and practical in functional programming, which is the invention of the F# language. It's not often that somebody gets to invent a new language which hits the mainstream. And this is a functional programming language which sits in the .NET environment. So it's a language in which you can develop serious commercial quality code. On the other hand, it uses the ideas of functional programming, which are what many students learn to love in their computer science education in university. So for the first time, students can actually use what they learnt at university not simply to understand in principle about programming, the nature of programming, but also in detail for assembling systems which, as I say, are commercially hardened. A couple of weeks ago, Don announced the latest development in F#, which is a new facility known as type providers. And without going into details here, because I don't have time, the importance of type providers is that they allow you from within the programming language to access the increasingly rich data which is available on the web. And it makes a somewhat effortless, compared with previous approaches, facility for accessing rich data. And this is going to be very important, for example, we believe, for scientists who are increasingly publishing their databases and wanting to compute with other people's databases, work on genetics, work on the environment, and many other branches of science. So that's just one of the areas of the lab. I'm going to sort of rush through the shape of the lab, if you like, in chronological order of the lab's construction, and the timeline kind of goes from the more core disciplines of computer science, the ones that you would expect to find in any university computing laboratory, to ones which I think are more adventurous in a way. So the next one, which I would think of still as being firmly in the core, is our systems and networking group. Ant Roosteren is the head of the group, and what's illustrated here is an architecture which he calls CamCube. And he and his colleagues are inspired by the problems of computing with big data, which are becoming, of course, more and more important to us. And so, of course, if you want to compute with big data, the structure of the data center that does the computing is very important. A conventional way to structure data centers is hierarchically with a tree of processors. And so what that means is that the path lengths between different pairs of processors are highly variable. In the worst case, one might have to travel all the way up the tree and all the way down again in order to communicate with between two processors. This structure here, they call it CamCube because it's a cube, but it's also a torus. I won't attempt to explain to you how it can be both a cube and a torus, but feel free to attack Ant in out in the public area there to get him to explain. But the upshot of it is that the communication paths between processors are very evenly distributed. In fact, no processor in this structure is special. There's no root of the node. Every processor is identical in the sense that, when you look at the horizon sitting on one of those processors, the landscape looks the same from any point. And this highly symmetrical arrangement turns out to be a powerful design for various tasks in computer science. For example, database access, one example that we've worked on. Another is inference over probabilistic graphs, a theme that will recur when I get to talk about machine learning and perception and indeed throughout the afternoon. The group has done research on peer-to-peer networking. For example, we licensed some of our technology to a company called Skinkers in 2006, which is now a leading business communications company. And you'll see various other communications issues, for example, white spaces arising from this group being discussed out in the public area there. Another development in this group is in is with the foundation of what we call the Network Economics and Algorithms group led by Peter Key. And this is to improve our understanding of online commerce, for example, online auctions, something that's highly relevant to our business, but also embodies fundamental problems. And this is a highly cross-disciplinary endeavor, which involves systems, networks people, also experts in economics. Some of these are academic partners outside the lab, experts in machine learning, and also experts from the Bing product group, which is one of the main stakeholders in this kind of work. So we have Joaquin Quiñonero Candela runs a piece of the Bing product group, but right alongside us here in the lab. And this is something which we particularly delighted that has grown up in the lab, that we have such close proximity to the product group. Indeed, Joaquin began as one of our own researchers and moved into the product group to set up this this activity, which is having very considerable influence in the company at large. And lastly, from systems and networks, we have a group run by Youssef Hamadi, which is working on constraint-based optimization. They've built a system that they call Dissolver, which is a generic set of tools to help people programming constraint optimization. For example, it's been used with what's called the SAGE software fuzzing tool, which is a way of generating random tests for software that's already been used widely in Office and Windows 7. Dissolver has also been distributed as part of what we call the Microsoft Solver Foundation, which is a library of tools, as I said, that's distributed outside the company and inside the company. Many Microsoft customers are using it, but also it's been used in a wide range of products, and you see some of them illustrated here. Most recently, Youssef and his team have been working on solving satisfiability problems in computer science, which is actually one of the core competences underlying formal verification. The Z3 theorem prover, which is something that a number of people in Microsoft work on. Youssef's team has contributed parallel algorithms to Z3, which has contributed to it winning this year's theorem prover competition in many of the categories. We're absolutely delighted with that. Well, in my chronology, the next group is machine learning and perception, which when it was established 14 years ago, right back at the beginning of the lab by Chris Bishop, he came so early in the evolution of the lab that the very first computers, desks and chairs were bought on his credit card. A couple of years later, he hired me, and work on machine learning. As I say, at the time, machine learning was not something you would find in every university computing laboratory, but I think it's increasingly the case now that you do expect to see it. The technology from machine learning and perception has contributed to a number of products. For example, in Xbox, the TrueSkill ranking came out of this group, which is the system used for maintaining global leagues for any game developer who develops for Xbox Live. So it's a kind of part of the agreement that if you're developing for Xbox Live, you use the TrueSkill system, and we're very proud that that came from here. There have been many contributions to Bing, not just from this lab, but across MSR generally, and MSR has had a major influence in the shape of Bing as it is now. But a number of those have come from here. For example, the way that sponsored adverts are served, and this is something that Joaquin Quiñonero Candela, who I referred to earlier, and his team are instrumental in. What else? Contributions to Office, the Path of Go game for Xbox, Kinect, which is this year's development, the fastest selling piece of hardware ever made, apparently, that is the eyes and ears of Xbox. It responds to human movement and makes the human body an input device, first of all for Xbox, but since then we've released a beta version for Windows PC in general, and later a version for a professional version for Windows is promised. Underlying a lot of what we do is a basic competence in machine learning, which we have encapsulated in this library that we call infer.net. And this is a major development both in science and engineering for us, which is gaining influence both outside the company and inside, and we are very excited about the possibilities for extending the influence of machine learning and having machine learning techniques become part of the mainstream of software development, both, as I say, inside the company and out. Another of the aspects of our work from the Machine Learning and Perception Group is the rather new computer vision image processing for medicine group led by Antonio Cremonesi, and there are some quite surprising juxtapositions of ideas here. Actually, medicine as a business has become very important for us as a company. We've made a major investment there. We have a substantial group now, the Healthcare Solutions Group, which is building a product that we call Amalga, which is a substrate for informatics in the hospital, supporting all of the computing that goes on in hospital databases, patient records, and so on. And Antonio is working on the imaging diagnostics in Amalga. And as I say, it's quite surprising that some of our work on object recognition, which we did rather speculatively because we were scientifically curious and wondered to what extent you could get a computer to recognize objects, has actually turned up and is proving to be very powerful in this context. And what Antonio and his group are doing is, as it were, recognizing objects from inside the body. And to understand why he's doing that, look out for his talk coming up a little bit later in the day. The fourth of the five groups was established by Ken Wood a number of years ago, and we call it computer mediated living. It's our version of a human-computer interaction group, but it's rather distinctive in the way that it's structured. One part of the group is led by Steve Hodges and concentrates on sensors and devices, being inventive about hardware. One of the things to come out of that, in collaboration with some of our colleagues in Redmond, is this design for the touch mouse, which won a prize in one of the main HCI conferences a couple of years ago, and more recently has been released as a product. The touch mouse pushed through to productization, largely thanks to Mitch Goldberg and his incubation group that he runs here in the Cambridge lab. And it's getting very strong reviews in the press. We're delighted about that. Another thing that the Sensors and Devices group have done is illustrated here. This is actually using the Kinect sensor that I mentioned before in a way that was really never intended for it, and that is to turn it into a portable device that you, handheld, that you move around an object of interest. It collects multiple 3D depth maps as it moves around the object and fuses them to get to capture a 3D shape in amazing detail, far greater detail than a single snapshot from the Kinect could do. So now for the $150 or so that one has to pay for a Kinect, one has a capability which previously would have cost probably a couple of orders of magnitude more. And this is, I think, a very exciting development. Now, the other part of the CML group that I want to tell you about is an interdisciplinary group that has a rather human perspective on computing. It's highly multidisciplinary. It has experts on design, experts with a background in psychology, in anthropology, and their view of life is that you should lead by understanding first what the human task is that's to be performed, rather than beginning with technology and asking what can the technology be used for, to, as I say, begin by defining the task, trying to understand what it is that humans are trying to achieve, and making the technology fit the task. And I think this is a very important theme which we're going to see more and more in computing, that computers, as it were, become less and less noticeable. As we become more successful in building devices based on computing, the computers should recede into the background, and the tasks and the things that humans are trying to achieve will become more prominent. The image here illustrates one project of this kind. It's called Family Archive. It's a central tabletop for the home where family memorabilia are captured and stored. We built a prototype in 2008, and now a second version is under development. Abby Sellen, who's one of the leaders of this part of the group, is going to talk to us a bit later about her way of doing business. And by the way, I'd like to congratulate her on just being elected a Fellow of the Royal Academy of Engineering in the 2011 cohort. Well, the last of our 5 groups is the computational science group, and I think it's fair to say this is not something that you'd expect to see in every computer science lab. I think it's going to be increasingly the case, however, that we will see more and more the combination of computer science and modelling that I mentioned earlier combined with biology. Stephen Emmett established this group here in the lab, and he's going to talk a little bit later in the afternoon about his ideas. Here we see Andrew Phillips, who leads one part of this group on biological modelling. One of the amazing things that he's working on is known as DNA strand displacement. And what this is about is a language which designs processes that happen in the medium of DNA. So this is really a gross abuse of DNA. Instead of making life out of DNA, this is taking DNA as an engineering machine in its own right and seeing exactly what kinds of computations, because indeed they are computations, that you can do by combining strands in different ways. And this is something that you really can experiment with now that you can send off, you go to the web and order a stream of bases to be delivered to your lab the next morning, 50 cents a base. I mean, it's just amazing now that you can play with DNA in this way. Andrew has just been awarded what's known as the TR35 Technology Review Award from MIT. This is an award that is to exemplify the spirit of innovation in business, technology and the arts, and we're very proud of Andrew for winning that award. The other part of the group that Stephen established is looking at environmental issues, and that part of the work is led by Drew Purvis. And here's an illustration of the kind of thing that they are thinking about. Of course, it's of paramount importance that we understand what is happening to carbon in our environment and what's going to happen over the years. And many scientists are putting in their very best efforts to try to estimate how carbon dioxide levels will change over the years. And here is a graph showing actually how much carbon dioxide will be absorbed by the planet in succeeding years. And the remarkable thing about this set of graphs is that they're shaped rather like a trumpet. You see, these models don't even agree on the sign of the change over time. It's absolutely astonishing with something that matters to us as much as this, that even the trend is not clear and the experts disagree amongst themselves about the trend. And what Drew and his colleagues are doing is trying to pinpoint some of the key elements that are missing from the models that people are commonly using and replace those missing elements to try to reduce this variance in the models. And they're getting amazing traction with that endeavour. Well, the last thing I want to say is that, harking back to the comment at the beginning about the 3 parts of our mission statement, that what we do proceeds from a basic expertise in research. And some people believe that if you have nigh on 1,000 people in your research labs around the world, that you should be able to answer pretty much any research question with that number. But actually, as you will appreciate and know, the world of ideas is very much bigger than that, and you just can't cover everything with only 1,000 people. And so it's critical for us that we work collaboratively with universities and scientists around the world. And here is an illustration of one of our programs. It's our PhD program. We've already funded 200 PhDs since we started, and this is the summer school that we held this year, where they all came to Cambridge to swap ideas and meet one another. And this is a very important program for us Many of the PhD students, who are usually co-supervised between somebody in the lab here and somebody in the relevant university, come and work with us as interns. Sometimes they come here as postdocs in the lab, and we even have a few now who've percolated all the way through the program and are researchers here. For example, our very own John Wynne, who is a senior researcher in the lab. So there we are. We're a basic research lab, but we're very proud, along with the other labs, to have had a profound effect on Microsoft business. And here you see many of the different products from Microsoft that have been influenced by Microsoft research, and in some cases defined by us. I have to say I'm really inspired whenever I talk to the people that we have here in the lab. Microsoft Research has been doing amazing things over the last 2 decades. I'm very excited to see what the next decade will bring, and I hope that all of you will enjoy hearing about and seeing the lab's innovations here in the lectures, out in the demos, as much as I do. Thank you very much.
Andrew Blake, great keynote there to get us going. So we're going to have a bit of a chit-chat now and meet actually a number of the characters that appeared there in Andrew's keynote. First of all,